the first lecture on membrane separation processes. We are going to look at some principles of membrane separation processes, and then later on we will go on to do some calculations. So first of all, some very basic nomenclature about membrane separation processes. So think about a module. Let me just put some pen. Yeah. So think about a module here. So this module is containing two compartments which are separated by a membrane. So membrane you can think of as a semi-permeable barrier. So what we supply to one side of the membrane, we call it as feed. Now some of the material will go through this membrane. We will call this as a permeate stream. Something will not go through this membrane, that we will call as retentate. Right? So what we are trying to filter or what we are trying to separate is some component from feed into two parts. One is the retentate and one is the permeate. Now let's talk a little bit about what kind of materials that are filtered by this membrane. Okay, so we had talked about sizes of different kinds of molecules. So for example, if you think about water, we had calculated what would be the size of the water molecule. So if you say water, it has a molecular weight of about 18. It has a size of something like 3 angstroms, 4 angstroms of that order. So it is in terms of nanometers. If you write, this is about 0.2 nanometers. If you take inorganic acids like say formic acid or inorganic acid like HCl or H2SO4 or HNO3, the sizes would be of ionic in nature, H plus ions or Cl minus ions. So those are of small molecular weights, and their sizes are also of the order of few angstroms, 0.2, 0.3, 0.4 nanometers. If you think about organic acids like acetic acid, formic acid, so acetic acid is something like molecular weight 100, acetic acid molecular weight is 60. So if you take that size, if you take that molecular weight and calculate the size, you will find that the size of an acetic acid molecule is about 4 angstroms, about 0.4 nanometers. So we had done all these calculations, so it's a good time now to revisit those calculations. If you look at some of the sugars, let's say for example glucose or sucrose, then you will find that they are much bigger in size, about 0.8 nanometers. If you go to bigger molecules, say proteins or enzymes, they have molecular weights of the order of thousands. They have molecular weight of the order of thousands, and you will see that their size of the molecule is about 2 nanometers. So the sizes that are calculated here, they are like approximate spherical molecule size. Now sometimes these proteins or polymers, they can be linear in shape, so it will have a smaller dimension in one axis and a bigger dimension in another axis. So this is only an approximate number, only an approximate idea to tell you what kind of sizes of different molecules that are there. So if you think about bacteria, you will have something like 0.2 microns. So 0.2 microns would be about 200 nanometers. So if you take blood cells, or if you take bigger organisms like yeast or fungi, they will have sizes of the order of millimeters and maybe several hundreds of micrometers. So when we are trying to filter some of these solutes from a solution, what is important is the size of these molecules. So for example, size could be really big or size could be really small. Now depending on that, we will have to design our membrane to make that separation. So now let's little bit more look at these sizes once again in a slightly different format. So if you see here size in terms of microns, so this is 1 micron, okay. This is 1000 microns, that is 1 millimeter. This is 0.001 micron, so that is 1 nanometer. So if you think about ions or simple molecules, they would be having a molecular weight less than 100. Their sizes would be in the range of 1 or 2 nanometer, 1 nanometer and below. If you want to separate those, we will have to separate them by a process wherein the size of the pores in the membrane are really small, and we call these processes as nanofiltration or reverse osmosis when we are separating ions from water. What you are accustomed to is in your undergraduate course, what you have studied is filtration. So those are big particles. So if you say 1000 microns, these are like 1 millimeter particles. And you have seen common kind of filtration media, so granular filtration, so sand or filter cloth. So these are all conventional filtrations. Now if you look at sizes of molecules which are of the order of, like say, enzymes or proteins, so you have sizes between thousands to 10,000s or 100,000 molecular weight. Their sizes would be something like 0.01 microns, meaning 10 nanometers to maybe 100 nanometers, or even if you say from 1 nanometer to about 100 nanometers, then you would have we would call that kind of filtration operation as ultrafiltration. So recall just the nomenclature. When we say microparticles, okay, then that's a particle, that's what you have studied in your undergraduate course. So microparticles, when you are filtering, that's called as a macro filtration. Whereas when you are filtering macromolecules or small particles, we call this as a microfiltration. So it is different from the pore sizes that we have studied in catalysis. When we looked at catalysis, we defined three kinds of pores: one mesoporous, microporous, and macroporous. So when it was macroporous, we had pore sizes about 50 nanometers and above. In microporous, pore sizes were less than 2 nanometers and above. So when you say microporous, the pore sizes are of the order of 2 nanometers. That means somewhere in this region, right? And then we call those as ultrafiltration or nanofiltration kind of operation. But if pore sizes are in the range of 50 nanometers, somewhere here, then we call this as macroporous, but we call it as a microfiltration. So little nomenclature we need to be aware of. These are the pore ranges that I was talking about: microporous, mesoporous, and macroporous. Okay. Let's go forward. So when we are trying to filter out solids or particles or molecules which are having sizes which we saw just now, we need different kinds of membranes. So one kind of membrane is called as a porous membrane. What this has is, you can think about this membrane being made of particles and gaps between these particles consisting of these can be thought of as pores. So now when solids are when you have feed on one side, so you have particles on one side, the solvent will go through this membrane, come to the other side, and particles would be retained by these pores. So these kinds of so if you look at this kind of membrane, the pores which are there, they are not uniform, but they are homogeneous, in the sense that no matter whether you look at the top part of the membrane, whether you look at the middle part of the membrane, or whether you look at the bottom part of the membrane, the pore sizes are approximately similar. Therefore these are called as symmetric membranes or isotropic membranes. Sometimes these pores are very small, or they are practically non-porous materials. Then these are called as dense membranes. So it is a dense in the sense that there are no pores, but there are no pores everywhere. So these are still called as symmetric membranes or isotropic membranes, but these are dense membranes. There are no pores inside. Now some of the membranes are anisotropic. We will soon see why we need an isotropic membrane. But if you look at this membrane, the pore sizes that are there in the top part of the membrane, in the middle part of the membrane, in the bottom part of the membrane, you can see the top part is made of fine particles, and the gap between them is also small. So you can think about this as pore size being very small in the top region, pore size gradually increases in the middle region, and pore sizes are very big in the bottom region. So these are pore sizes which are not uniform across the cross section. Therefore these are called as non-symmetric or asymmetric membranes, or sometimes they are called as anisotropic membranes. So when you had done filtration in your undergraduate course, you had seen that, let's say, your filter cloth was something like this, and you had a thicker filter cloth or a thinner filter cloth. When you had a thinner filter cloth, your filtration rate was higher. That's because the resistance offered by this cloth or by this membrane was proportional to the thickness of that membrane. So now imagine that we are trying to filter out small particles. So therefore we need very small pore sizes, and then if we have a membrane which is thick, then we will require a very large pressure drop, or the filtration flux would be very small. So the option to get high filtration rate is to have a very thin membrane, right? But if you make the membrane very thin, then it is structurally very weak. It can tear off or it can break very easily. Therefore, we need to make an isotropic membrane where this would be a kind of a support on which this thin layer, which has very small pore size, sits. So now filtration now is being done by this small layer called as active layer if you want, and this active layer is resting on a support. So when this Loeb and Saurirajan made this kind of membrane in 1960s, they were the pioneers and the first one to make these kinds of anisotropic membranes, and this allowed membrane, the active layer of the membrane, to be very thick, yet because of the support this membrane can be structurally strong, and they could create modules out of this kind of membrane for reverse osmosis applications, and that allowed very high flux at reasonable pressure drops, and this really paved the way for membranes to be used in a commercial manner. Sometimes you may have two different kinds of layers in a membrane. So you would have a support layer made of one material, and you could have an active layer in the form of a very thin film deposited on this support. So these are membranes made of different materials, right? And therefore these are called as anisotropic, but they are made from thin films, and it's a composite of a thin film and a support. Therefore these are called as thin film composite membranes, or thin film. Invariably they would be anisotropic membranes. Sometimes the membranes could be charged membranes. So for example, think about a membrane which is made of polymers, and this polymer has a let's say carboxyl ion on its matrix. So this will have anion charged membrane. So this would be an anion charged membrane, but it would allow cations to travel from one side to another side. So if you apply electrical potential, cations could go from one end of the membrane to the other end of the membrane. So it will allow cations to flow through the membrane. So these could also be called as ion exchange membranes, and these play a very important role in electrolysis application or in fuel cell application, where you want protons to go from one part of the one electrolyte to another electrolyte, and these would be these kinds of membranes would be used. We had seen supported liquid membranes. So we had a macroporous or microporous support in which we had pores, and these pores were filled with a liquid. So you remember this, we had seen this when we were talking about liquid extraction. When we were talking about extraction of cobalt ions from aqueous phase into another aqueous phase, strip phase, when this was being filled with a liquid cation exchanger membrane, and then cations would go from the feed side to this membrane, and H plus ions would come back, and then these the cobalt ions, let's say, that were here, went into the strip phase, and an H plus ion would go from the strip phase back into the liquid phase. So these are called as supported liquid membranes. We had already seen this when we had done liquid extraction. Okay, let's go forward. If you have any difficulty at any point of time, it's a good idea to pause and think, and pause and read up extra material, and then continue the video. Let's go a little forward. Just wait for a second. Yeah, so when we are trying to look at the transport mechanism, we have looked at two kinds of membranes, porous membranes and dense membranes. So porous membranes has pores in it. So think about this as a membrane. This has one pore in the membrane. So this is one pore. Now imagine on one side we have molecules of different size. Let's say, so this could be a solvent and this could be big particles, let's say sugar molecules or enzyme or a protein. Now you will obviously see that it depends very much on what this pore size is, and size of the pore as compared to the size of the solvent and size of the molecules that are being filtered. So if your pore size is small, you will have small molecules which can go through easily, but the big molecules will be retained in the on the field side of the membrane. Whereas when you say dense membrane, there are no pores inside. So even if there are two molecules which are of any size, they are not going to be able to go through the other side unless this particular molecule, let's say we have two kinds of molecules, one this kind and one this kind. So let's call this as A and B. So if we say that this A molecule has a preferential solubility in the membrane, then this molecule will dissolve in the membrane, it will diffuse through the membrane, and then it will come out through the other side. Whereas if B has less solubility in the membrane, it will dissolve to a very little extent or not dissolve at all, and then this B will be retained on the field side and A will go through the membrane to the other side. So this way you will be able to separate A and B from using a dense membrane. So at this point it will be a good idea if you can think about what different factors will influence the rate at which molecules will go from one end to the other end for a porous membrane, and what factors which will affect membrane, which will affect the flow of, let's say, A or B to the membrane, through the membrane from one side to the other side. So just take a break, pause the video and try to list as many factors as you can here. Okay, and we will see in our next lecture what kind of factors are important in these particular processes. So just to summarize what we have all seen just now, we had seen that if pore diameters and the size of the molecules will decide what kind of filtration mechanism or what kind of membrane filtration will be taking place. So if pore size is very big, let's say, so this is in terms of angstroms, so this is like a 1000 angstroms is like 100 nanometers. We will be able to filter out big particles. These are called as microfiltration application. If pore sizes are of the order of 100 angstroms, which means tens of nanometers, we call this as an ultra filtration operation. If pore sizes are of the order of 10 angstroms, which means 1 nanometer and below, we call these as nanofiltration. And if the pore sizes are very small or it's a dense membrane, then we call these operations as reverse osmosis kind of operation, where we are separating essentially ions from water. So here you would be separating small solid molecular weight 300, 400, 500. Here you would be separating molecular weights, enzymes, proteins, molecular weights of the order of thousands, 10,000s, 100,000 and so on and so forth. And we will see these different kinds of mechanisms. So if you see pore sizes which are about 1 nanometer, here we have pore flow kind of mechanism. Pores big and molecules are able to flow through membrane by through these pores. Whereas if you go to pore sizes which are very small, then these are like dense membranes and you are able to separate the two components based on some property which we will see later on. So this complete sort of introduction to different kinds of membrane processes. Just before we close, it is a good idea to recall and go back into the lecture and try to look at different processes: microfiltration, ultrafiltration, nanofiltration, gas separation, reverse osmosis, pervaporation, facilitated transport. Try to write the driving force here and try to write the size of the solute. So by you can go back and forth through this video and make this table complete so that it re-emphasizes all concepts looked at. In the next class, what we will try to look at is individual mechanisms now. So we will look at the pore flow mechanism first and then we will look at the dense membranes.